October 2014 marked the 50th anniversary of one of Japan's great engineering triumphs, the Shinkansen high-speed railway. The Tohoku Shinkansen, which connects Tokyo to northern Japan, can reach speeds of 320 kilometers per hour. That puts it on par with France's TGV. Japan service is just as famous for its safety and punctuality. Railway experts around the world are paying close attention to the Japanese high-speed railway system. After half a century of improvements and innovations, Japan's engineers have pushed the train to a level no one has ever achieved. They've developed the world's leading technologies to cut noise, conserve energy, and reduce weight. And now, they're aiming to make the Shinkansen bullet train even faster. Japanese rail companies and manufacturers are trying to tap into international markets. We look back at the history of Japanese Shinkansen technologies and explore possibilities of how those original technologies can be exported to other countries.
I'm a big fan of trains. I love the ones running in Japan, as well as the ones in Great Britain, where I'm from. In Japan, there are a wide variety of trains, from local, antique-looking ones to state-of-the-art ones like the Shinkansen. The view from the train windows of Japanese trains changes from the city to the sea, then mountains, which I enjoy very much.
Professor Anthony Robbins is a member of the UK-based Japanese Railway Society. The group has around 200 members in the United States, Germany, Holland, and other countries. Professor Robbins and other enthusiasts ride Japanese railways across the country.
In this program, we are going to consider 2 points. The first is how the Japanese Shinkansen successfully gained a high standard in 3 areas: speed, safety, and punctuality. Secondly, how far the technology Japan has developed is contributing to the country's exports, while the demand worldwide for high-speed trains is increasing. First, let's have a look at how the 3 points, speed, safety, and punctuality, were accomplished.
The train made its debut in 1964, the year Tokyo hosted the Summer Olympics. With a top speed of 210 kilometers per hour, people could arrive in Osaka from Tokyo in 3.5 hours. Until then, the trip took 7 hours. The economic effect of the shortened travel time to the nation came to an estimated 250 billion yen. The Shinkansen became a $1 million line in a matter of seconds. There are 8 lines in total, servicing a network of 2,663 kilometers. Routes are spread all over the country. In 2015, the Hokuriku Shinkansen will begin service on the Japan seacoast, expanding the network to 2,900 kilometers. Speed has been increasing as well. Shinkansen travel more than 100 kilometers per hour faster than in their debut. They arrive at their destination on time with hardly any delays, and there still hasn't been a single fatal collision or derailment. Of primary importance to the Japanese high-speed railway system is crash avoidance. This lies at the core of technological development. Shinkansen run on specially designed tracks separate from local and freight trains in order to meet crash avoidance integrity. This eliminates the risk of collisions with other trains and accidents with people and vehicles at rail crossings. When the Shinkansen debuted, only 60 trains departed daily. Now, that figure is 323. Bullet trains depart every 3 minutes from Tokyo Station during peak hours. The Shinkansen emits 1/8 the CO2 of a single automobile, and it can accommodate more than 1,300 passengers, far more than the largest aircraft. The Shinkansen is considered a world leader in eco-friendly, energy-saving transportation. After the breakup and privatization of Japan's railways in the 1990s, the country's rail operators set themselves the goal of a bullet train that could travel at 300 kilometers an hour. Japanese trains had fallen behind France in the high-speed rail race. The French had achieved 260 kilometers an hour, but Japanese companies set their sights even higher. Their aim, an operating speed of 270 kilometers per hour, 2.5 hours between Tokyo and Osaka, trying to win back passengers from airplanes. At that time, it took an hour to get to Osaka from Tokyo by air, but an extra 1.5 hours to travel to the airport and for check-in. The Shinkansen operator was confident they still stood a good chance. The first area of focus was a reduction in weight. The new model would have to be 20 tons lighter than the original 64-ton Zero Series. Aluminum was used instead of iron in the body. The early models had a strong inner frame and an outer wall attached by rivets. This increased air resistance, slowing the trains down. So engineers set about finding another way to build them. They came up with the idea of using thin aluminum sheets and molding the inner and outer walls together. A 40% weight reduction was achieved. Air resistance was also reduced. And they switched the kind of motors they were using, making the trains even lighter.
In the first place, an AC motor weighs less if it can output the same power as a DC motor.
A change in the direction of electric current is necessary for a motor to operate. However, some old Shinkansen models ran with DC motors because AC motors would make it extremely difficult to control the speed. Since the beginning, AC electricity was flowing through transmission lines and converted into DC to turn the DC motors.
No one thought it was possible to use the DC motors for railways before the 70s. But in the 80s, with the inverter system, they were commonly used.
Here is how the inverter operates. To make the motor on the right turn, we need to change the flow of electricity by switching over between A and B. Usually this occurs over 50 times a second in Eastern Japan and Europe. It is the inverter that changes the frequency of switchover. To make a train run faster, increase the frequency. On the other hand, to slow down, reduce the frequency to control the speed. Thanks to the inverter, DC motors were able to change speeds. Many test runs of aluminum-bodied trains and DC motors were conducted at night. And on February 28, 1991, 325.7 kilometers per hour. A new chapter for Japanese railways began in 1992, when a slimmed-down series commenced services and ran between Tokyo and Osaka in just over 2.5 hours. As railway operators had predicted, the extra speed attracted more customers. More than 130 million tickets were sold annually throughout the 1990s. In 1997, a new model was developed with a maximum speed of 300 kilometers per hour. It connected Tokyo and cities like Hiroshima and Okayama over 700 kilometers away, further cutting into the advantage enjoyed by airlines. The 500 series. The first carriage was 27 meters long and featured a streamlined shape. The 500 series kept the height of the cars the same as the 300 series, but lost a skirt at the bottom of the body. Baggage compartment space and other non-essentials were kept to a comfortable minimum. As a result, a 10% reduction in cross-section was achieved, making the 500 series 10.2 square meters smaller than the 300 series. Furthermore, the body needed to be stronger to run at 300 kilometers per hour. So the designers created a double outer wall. This also helped reduce the noise level inside the cabin. It was now possible to travel between Tokyo and Hakata in an amazing 4 hours and 49 minutes. The 500 series also overtook the French and reclaimed the world's fastest operation title.
Such history made the Shinkansen what it looks like now, featuring a unique and beautifully shaped body. The Japanese Shinkansen is rarely delayed. Let's find out why.
In the past, it was not unusual for high-speed trains to experience weather delays, especially snow or heavy rain. Today, the Shinkansen's average delay is under 1 minute, making it the most punctual high-speed railway in the world. A control system makes it possible for a high-speed railway to run trains at 3-minute intervals during rush hour and with hardly any delays.
The Tokaido Shinkansen line has the automatic train control system. It's the most important among the specific features equipped with this high-speed railway line.
The ATC enables the train to calculate an appropriate speed based on information transmitted through the rail on its own position and its distance to the preceding train. A long route has gradients and curves. Various data concerning the conditions of the entire route are stored in the ATC. The conductor finally adjusts the train speed for accurate operation by watching the permissible speed on the ATC and figuring out the remaining minutes and distance to the next station. In February 2013, the N700A was introduced to the Tokaido Shinkansen. A stands for Advanced. Prior to the introduction of the N700A, the ATC had become digital.
The previous generation of ATC was the multi-stage ATC. Speeds were controlled according to the position of the preceding train on a certain section of the track. It wasn't possible to immediately reduce speed.
When reducing train speed from 270 kilometers per hour, the traditional ATC needed to work in several steps. First, decelerate to 230 kilometers per hour before decelerating further to 170 kilometers per hour after running for a certain distance to stabilize the speed. The digital ATC cleared up this problem with the ability to reduce train speed at once. The digital ATC can recognize the positions of the preceding and following trains. Speed can be reduced in less time and distance, decreasing the frequency of applying brakes as well. This enabled shortened departure intervals, allowing for an increase in the number of trains in service. The digital ATC is not the only aspect of the evolution of the N700A. There's also a system to travel at regular speeds. The driver always finally adjusts the speed, but when a delay occurs due to unpredictable events such as torrential rain, the train gets mechanical support for its operation in line with the ATC signals. This enables prompt recovery from delays.
Because a high-speed train has higher running resistance, deceleration greatly reduces train speed. Since there are many conditions, such as gradients, there is a limit to human control for maintaining constant train speed.
By using this system, delays can be reduced to a minimum. There are 8 Shinkansen lines where various types of trains are running. The N700 series runs through Japan's main artery. This series was developed aiming to provide high-speed, comfortable, and more environment-friendly service. In 1997, the 500 series beat the average speed record then held by France's TGV and became the fastest train in the world. Currently, it's in operation between Osaka and Hakata. The E4 series, connecting Tokyo and Niigata, features completely bi-level train sets. A 16-car formation train set has a seating capacity of more than 1,600, the largest in the world. The E5 series, connecting Tokyo and Aomori, has a maximum speed of 320 kilometers per hour, the same as the TGV. A superior first-class car has been introduced for the first time in Japan. The E3 series connects Tokyo and Shinjo in Yamagata Prefecture. Trains are slightly smaller and run on a narrower conventional track from Fukushima Station. The E6 series connects Tokyo and Akita in the north. These trains run on both the Shinkansen track and the conventional railway track. The E7 series currently connects Tokyo and Nagano. These trains have excellent gradability, enabling them to run through mountainous regions. The 800 series travels across the steepest slope in the rapid transit network. The interior features traditional design and regional materials.
The Shinkansen technology developed over the last half-century now aims for the world railway market. With increasing worries about global warming and rising CO2 emissions, the world is shifting towards high-speed trains. Worldwide, makers are paying close attention to the market. Does the Japanese Shinkansen have a good business chance?
High-speed rail planning is currently underway in 29 countries around the world. The Asian market features a total distance of 10,000 kilometers, around 4 times the coverage of the Shinkansen network in Japan. Railway companies in Europe also have their eye on this market. What Japan has in mind is not just exporting train cars alone. It's a package of hardware and software as well as basic infrastructure, such as exclusive tracks for Shinkansen and the ATC system. Japanese railway companies operating high-speed trains and related manufacturers are joining hands to export Shinkansen technology. In mid-October, they invited about 300 overseas government and industry officials to Tokyo to promote the technological capability of Shinkansen as one unified system.
So these are quite different projects, quite different geographies, quite different people, quite different countries, different backgrounds, and we're going to tease out some of the similarities and the differences in the course of our discussion this afternoon.
During the conference, each country's high-speed railway program and its progress, as well as the Shinkansen's valuation in each program, were presented. Singapore is planning to build a 350-kilometer international high-speed railway across the border to Malaysia.
Well, I think, let me start by saying that with the Japanese Shinkansen system, you have a system that is the envy of many in the world. I think it shows that you design the system with a person in mind, that the personal experience riding on it is more than just about taking a ride, but actually the whole experience. And I think that says a lot about the Japanese Shinkansen system. Unique situation where there's a whole lot of the Japanese industry in Japan here that's supporting the Shinkansen system, whether it's a rolling stock manufacturer, or whether it's the single links, or the tribal or civil infrastructure. You do have all these support systems. But so come the two other areas that I was planning to say, which is affordability. So other than all the tangible things involved, I think at the end of the day, to the commuter, there's also the affordability.
Japanese-type high-speed railways assume the construction of separate tracks. This requires a lot of land and funds, about $70 million per kilometer. From this standpoint, the Japanese side is looking toward the United States with great expectations. High-speed railway planning is taking place in 4 regions. In California, a high-speed line connecting Los Angeles and San Francisco is scheduled to open in 2029. In September this year, the vice president of East Japan Railway Company paid a visit to promote the Shinkansen's safety, accuracy, and economic benefits. In Dallas and Houston in the state of Texas, continuous marketing activities to enable the introduction of the N700i Bullet, the overseas model of the Tokaido Shinkansen, are underway. Local media are commenting on the benefit of Shinkansen technology. They sound as if a contract were already in place.
We're excited about it for several reasons. First of all, because it's just cool, okay?
Well, I think what attracts people in Texas to the Japanese model is, number one, safety. Number two is the certainty of schedule use. I think Americans have about 600 automobiles per 1,000. It's the highest average in the world by far. And in Texas, it's higher than it is in most places in the rest of the United States. So you have a situation in which anything you can do to help the environment and reduce the carbon emissions is going to be greatly appreciated and will come right into the rest of the economy. So high-speed rail is really attractive from the environmental.
Prime Minister Shinzo Abe also got behind the marketing push.
When the Shinkansen line opened in 1964, Japan was still poor. We were short of money. So we borrowed from the World Bank to build the Shinkansen line. We are keenly aware that we did not do this alone. We owe a lot to people around the world for their cooperation. We have kept this firmly in our mind and have been grateful. From now on, in a way to return, we are hoping to contribute to a better future of the world through our technology and financial cooperation.
In some areas, the Shinkansen has already begun operating. Taiwan. Initially, a consortium of German and French manufacturers won the order, and the rail development started in 1997. But 1 year later, a derailment of the German high-speed railway ICE brought heightened attention to the safety of the Shinkansen, and Japan took over the project. The driving system of the Shinkansen was also suitable in Taiwan. The Shinkansen utilizes a power-dispersed system. All the cars except the front and rear are equipped with motors. Compared with the power-concentrated system used by Europe and the United States, in which the very front car pulls the rest of the train, this system is appropriate for uneven routes. The power-dispersed system is a technology built up over half a century in an effort to operate stable train services even on the steep slopes scattered across Japan. And that was a perfect system for Taiwan with a similar geography. Today, high-speed trains based on the 700 series of the Tokaido Shinkansen are in operation here. They connect the 345 kilometers between the north and south of Taiwan in 90 minutes, running at a maximum speed of 300 kilometers per hour. Train cars featuring Shinkansen technology were also exported to the United Kingdom. The Japanese-made Class 395 runs on the high-speed rail HS1 that became available along the entire line in 2007. It was manufactured in Yamaguchi Prefecture. The aluminum body manufacturing technology developed through reducing the weight of the Shinkansen was used in the Class 395. Unlike in Japan, the high-speed rail systems in Europe and the United States don't have their own tracks, but share the routes with conventional trains. For this reason, the train body needs to be strong enough to deal with possible collisions. The train cars manufactured for the UK's HS1 were designed in accordance with UK standards in many ways, such as strength and noise control measures. As a result, the conversion of aluminum train body manufacturing technology and export market standards has led to the creation of a new technology export model.
If different railway systems abroad get improved in the future, I would say that Japanese train body manufacturers and our various related technologies may be able to contribute to them again. If that happens, we can see it as an overseas expansion of the industry as a whole.
Japan seeks to export another groundbreaking technology. With current high-speed railway systems, the construction of tunnel sections is increasingly being considered in order to preserve scenery and the environment. In the late 1990s, when the Shinkansen reached speeds of 270 kilometers per hour, a serious problem specific to tunnels emerged. The noise that occurred when it passed through the tunnel. When the train entered the tunnel at high speed, the noise occurred repeatedly near the exit. Technology to cope with the tunnel issue made dramatic progress by solving this noise problem. Professor Takanobu Ogawa of Seikei University, an expert on airflow inside high-speed tunnels, says the front shape of Shinkansen cars greatly influences the tunnel noise.
When a train moves into a tunnel, the air inside the tunnel is compressed by this train, and then a pressure is formed inside the tunnel. This pressure wave goes through the tunnel exit. A booming noise is generated. So this is the mechanism of a booming noise. This phenomenon is similar to the sound generation by a pop gun. When you press a piston of this pop gun, the pressure inside the gun increases. Then cork breath goes off. The high pressure inside the gun is released, and you hear the sound of pop.
Professor Ogawa is working with an outside company on this issue. This 40-meter-long linear course is at 1/33rd scale of the actual size of the high-speed railway. A tunnel is included as well. Two models, old and new, will run at equivalent Shinkansen speeds. A sensor is placed at the end of the tunnel to measure the variation in air pressure. First, the old model.
3, 2, 1, 0.
The sensor catches a distinct increase in air pressure when the model enters and before it comes out. This peak part is the moment when the booming noise occurred. The duckbill shape is thought to be the best solution. Now, a test run with the duckbill shape model.
3, 2, 1, 0.
A similar result. The air pressure increased when it entered the tunnel and reached the peak right before the front of the model reached the exit.
This is a boom noise of the conventional shape, and this is the one for the duckbill shape. It actually has two peaks here. The boom noise is reduced by about 30%. This conventional train shape has a sharp nose and looks better for low boom noise, but this shape creates a strong flow speed. On the other hand, this optimized train shape has a blunt nose and shoulder, which distribute the flow speed almost evenly. In order to connect cities by high-speed trains at like 300 km per hour, we may need to build more tunnels, even in Europe and North and South America and Asia. And we have been studying the tunnel noise problem over the last 50 years. And I think that Japan has advantages in the world high-speed railway development.
Japanese railway people discovered that the aerodynamic characteristics of the first car were the key to solving an air resistance issue. Not just the overall design, but the bullet nose styling was what made solving this possible.
A high school in the center of Tokyo where young would-be scientists gather. We asked the students to test the aerodynamic characteristics of the nose shape of the Shinkansen models. First, the old model. Holes are made in the model to measure air resistance. Tubes are inserted into the holes. We will measure the air pressure these areas encounter by observing the level of the colored water at the end of the tubes. Each tube is numbered, corresponding to the respective hole location on the model. The test begins. A blast of air at 150 kilometers per hour is released toward the old model Shinkansen. The air pressure at the measuring points is recorded in the tubes. The original level was 166 millimeters. Where more air resistance was measured, the water level fell. With less air resistance, the level rose. Next up is the new model Shinkansen.
Number 9 and 10 show proper air resistance, which means the air goes upward properly. The measurements for the 0 series are irregular, with plus and minus mixed up. It gets unusual air pressure from various directions. Also, levitation and a forward resistance force against propulsion is added.
The students will now look at the air streams moving horizontally along both sides of the train. While the old model creates air streams to push out the air, the new model exhibits hardly any.
The Tokaido Shinkansen line has a lot of unfavorable conditions, such as many curves, tunnels, and steep slopes. I thought that they have become that technologically sophisticated by running trains on the track at high speed.
The front of the Shinkansen represents the history of engineers and their battle with aerodynamics. A first-generation train had a nose of about 4.5 meters. As Shinkansen trains sped up, their noses became sharper, as if they were shaved by the air. The longest nose is about 15 meters, belonging to the 500 series, which holds the record of the world's fastest average speed. The design inspiration comes from the kingfisher, which dives into the water to catch its prey. With the 700 series, the design underwent a complete change to a more relaxed shape resembling a platypus. However, as a skilled hawk hides its talons, the aerodynamic characteristics were the best of all. Tunnel noise was significantly reduced. The platypus-shaped nose is also present on the latest N700A series. The latest train has superior aerodynamic characteristics, achieving a 30% cut in air resistance from the first-generation trains when traveling at 200 kilometers per hour. In addition, with the introduction of streamlined train cars, annual electricity consumption was reduced by 16% over the 12 years between 1990 and 2002. This evolution has also resulted in the byproduct of energy conservation. Shinkansen trains that head from Tokyo to Aomori in the north travel at a speed of 320 kilometers an hour, the same as France's TGV. The trains cover the distance of 670 kilometers in 2 hours and 59 minutes. The E5 series also features a platypus shape. Its sloped nose is 15 meters long.
Before we produced the E5 series with the platypus-type nose, we made an experimental train car of that type and one with a sharper nose and compared the two in test runs. We found that the platypus type has less air resistance.
An E6 train running between Tokyo and Akita. As far as Morioka, it is linked with the E5 and runs on the separate Shinkansen track. From there, it begins to run on the conventional track. The E6 runs at a speed of 320 kilometers per hour, but its nose section is 13 meters long, shorter than the E5's. How could the nose be shorter, yet achieve this speed? The whole car is about 30 centimeters narrower. This results in reduced air resistance. The E6 runs on both the conventional and Shinkansen tracks. It features various original technology. For instance, the driver's seat. When the train is on the conventional line, the driver has to confirm crossings and signals with his own eyes. Visibility tests were repeated many times to determine the ultimate position of the driver's seat.
All Shinkansen lines are about 20 meters long. But this one runs on the conventional line, so we have to keep its width to less than 3 meters. But since it also runs on the separate Shinkansen line, we cannot reduce its equipment. So we made the equipment into a compact size and put it onto the train. But it also runs on the conventional line, so we need to put equipment for that onto the train too.
E6 Shinkansen trains can be said to be an omnibus of Japan's industrial technology. That is, the art of making everything smaller and compact. And today, Maglev Chuo Shinkansen has begun moving forward as the technology to open up a new era of high-speed trains. In 2027, a dream super express for a new age will begin operation at a speed of 500 kilometers per hour, twice as fast as current trains. In 2003, the magnetic levitation Shinkansen achieved a speed of 581 kilometers per hour, recapturing the title of fastest train in the world. Superconductivity is the technology behind such high-speed train operation. Superconductivity in general can be achieved by cooling a certain material to an ultra-low temperature to create a state where the material becomes extremely conductive. This is a model to show the mechanism of superconductivity, though the actual maglev Shinkansen uses a completely different system. Alternating N and S magnets are installed on the track. A superconductive material is installed within the white case and cooled to a temperature of minus 196 degrees Celsius. When in a superconductive state, the material obtains a property to memorize a magnetic field, the force surrounding a magnet. Hence, a superconductive material can keep itself afloat as shown here. When it is moved above a rail track similar to that of a roller coaster, it travels above the track, floating without dropping. With the application of such superconductive force, the Shinkansen can travel above the track while staying afloat. However, because this traveling force is merely generated by the initial inertia, it cannot climb the upslope located at the end of the track. The actual maglev Shinkansen uses alternating N-pole and S-pole superconductive magnets on train cars to generate a combination of repulsion and attraction forces, which pulls the train cars forward. As the train gains speed, a thrust force and a lifting force are generated, and train cars lift up by about 10 centimeters. After 8.8 kilometers, the train speed exceeds 500 kilometers per hour. Because it uses magnetic repulsion and attraction, a train can always maintain its relative position to a rail track. The technology is less susceptible to sudden occurrences, such as an earthquake. On into the future, trains are expected to aim for even faster speeds. This is giving rise to further challenges. It may become difficult to take much more electricity from pantographs. What will happen if rail friction becomes more serious? Central Japan Railway Company, the operator of the Maglev Shinkansen line, says their technology can lead to a breakthrough in meeting those and many other challenges. Japan is targeting a railway line between Washington, D.C. and New York, the centers of politics and economy in the United States. In April, Prime Minister Abe invited U.S. Ambassador Caroline Kennedy to the Yamanashi Maglev test line. Top-level sales talks were suggested.
So how high is the limitation? どれくらい高く浮上してるんですか? 10 centimeters. 10 centimeters. There, I saw it, I saw it, I saw it, I saw it. That was a wonderful ride, and I think that this technology is something that will bring great benefits to Japan.
Now there is great interest in high-speed rail. This was triggered by the success of the Japanese Shinkansen, the original high-speed rail system. A faster, safer, and even more punctual Shinkansen has been the result of overcoming problems and constant improvement to make Japanese railway technology ever better. Now the Shinkansen is in competition to operate various high-speed systems around the world. In order to win this global competition, Japanese makers will face many challenges. I believe they can overcome these challenges with their knowledge and effort, building on their successful operation of the Shinkansen in Japan for 50 years.